Well, hello there, boys and girls. You took me by surprise. Hi, I'm Mikey Lankenau, and this is how you do math.
Oh, look at the doggies, they're so cute. Hey, Chucky. Hey, Chucker. Hey, Sadie. Oh, they're fighting. They're fighting. Oh, they're so cute.
Oh, hey! Didn't see you there. In today's episode, we will be calculating the average rate of change. Let's take a look at problem number 1. Come here, Jay. For this problem, we're looking at the years and the product produced during those years, represented by P, which can stand for pencil shavings. So, let's find the average rate of growth from 1991 to 1995. So, your normal slope formula, I'll do over here, be y2 minus y1 over x2 minus x1. So for this, since product, very good, since product would represent the y values, we're going to use the product numbers from 1995, which would be the x2, and from 1991, which would be the x1. So, sorry about that, folks. Sorry about that. So, 1995, we will use 839 minus 793 over, sorry, that was a pretty bad line, 1995 minus 1991. Or you could just use 5 and 1, either works. So, sorry, according to my calculations...
You're smart.
Well, thank you, Jack, thank you. It's all in the glasses. Yes, glasses. Our answer would be 11.5 pencil shavings per year. Now, for part 2, we're going to have to do 1993 to 1995. So, if this was instantaneous, it would just be one equation throughout the whole line, and you just plug in different x values. But, since we're finding the average rate of growth between two different points, it's going to change. So, for 1995, we would still use 839, but this time minus 820. And this would be over 1995 minus 1993. And according to my calculations, 1 second, folks, 1 second. It's 5 minus 3 is 2. Okay, 2.
You're smart.
Thank you, Jack. It's all in the glasses. 9.5 pencil shavings. Sorry about the left hand, folks. I know it's a burden. Per year. Now, folks, we only got one more to go for problem number 1. Step 3, from 1995 to 1997. So, same y2 minus y1 over x2 minus x1. Same old thing. So you're getting the hang of it now, getting the hang of it?
Not really.
Jack's not getting the hang of it, and Jack's in the 7th grade. He'll get there soon. Okay, so we'll use those two values. These are the p values, which are the y values. We'll do 1997 over 1995. Sorry, it's hard to see in these glasses. So that was 974 minus 839 over 2. That does not seem right. Okay. And for this one, we will have 67.5 pencil shavings per year. If this is wrong, Miss Penson, I am sorry. And that is how you do problem number 1. Get over here, Jack. We gotta do problem number 2 right away. Okay. So, problem number 2, we're given a velocity function. All right, sorry about that. 2t squared minus 3.
Pencils?
Minus 3. 4-point Oakton, gotta represent. Good stuff. All right, calculate average rate of change from t equals 2 to t equals 6. So, folks, this is very similar to the one we just did before. These t values here, yes, right there. And these Jack, stop. These t values are just like the years in the other problem, but for this one, we are not given a table with the values, so we're going to have to calculate them ourselves. So for now, but it's the same formula, the y2, here, let me write this up here, the y2 minus y1 over x2 minus x1, simple slope formula. Got that, very good, I got that, that's enough. Okay, so for y2, for now, I'm just going to say, represent it like this, v, sorry about that, that's wrong, v of 6 minus v of 2 over 6 minus 2. And v of 6 in this case, using my very fast mental math, would be 69 minus a 5 over 6 minus 2, which equals 4. So 64 divided by 4 is 16. And folks, sorry about that, folks. My little brother Jack here accidentally turned off the recording, so we're just going to start where we left off. So what I was saying is very important. Don't forget, which I almost did, is that this velocity function, we're just putting in a time, so it's in meters per second, because that is velocity. And it's saying t equals 2 to t equals 6, so these values down here are going to be seconds. So once we divide it all out, it is going to be 16 meters per second squared, which is, Jack? Acceleration, very good, acceleration. So, that would be the answer for part A. Jack, back to the paper. Alright, so, now we're going to have a bit of a trick problem. Thank you, Jack. It's all in the glasses. Calculate instantaneous rate of change at t equals 5. So you see, get t equals 5. There you go, okay. So you see, folks, in this case, it's not from one point to another, okay? It is just that one point, and we're going to need a function to put that in. So, if we've learned anything from calculus, it's that in order to solve this sort of problem, we're going to need to find the derivative. So, the derivative of t, which actually is just acceleration t. And let's figure this out, folks. A of t would equal, let's use our exponent rule, just 4t. 4t, that's it. So, if we want to find from t equals 5, we are going to do a of 5 equals 4 times 5, which equals 20 in its acceleration. So the units would be, Jack? Meters per second squared, that's correct. Thank you, Jack, thank you. So, at t equals 5, the acceleration is 20 meters per second. Not between two certain points, but at that value. And that is the beauty of using the derivative to find the instantaneous rate of change. A little tip for you folks out there. Don't quite know your calculus. That's it. Jack! Come here, quick! We gotta do problem number 3 right away. Come on! Okay, so for problem number 3, we got a word problem, so these can be a bit of a toughie. So let me read this out for you. The displacement of a particle moving in a straight line is given by s equals t squared minus 8t plus 18, where t is measured in seconds. Find the average velocities underlined, get that, underlined, very important. We'll see why, bit, over the time interval 3 to 4. So folks, this time interval 3, 4, these are both x values, which will be in the unit time, seconds. So, start writing this out. So, just like the other problems here, well, actually in this one we have a function and an interval. So, what we're going to need to do is find the average velocities. So, in order to do that, we got to plug in the x values into the position function, because when we finally do our slope formula, we will have meters over seconds, which will give us average velocities, because velocities is in meters per second. Hang in there, Jack, hang in there. So for the first one, we're going to use 4, plug it into the position function, 4 squared minus 8 times 4 plus 18 equals 2. And the other one, S3, 3 squared minus 8 times 3 plus 18 equals 3. Let me check my math here real quick, folks. Get that TI action in there. And that will give me positive 2. Very good. 3 squared minus 24 plus 18. Does that give me 3, Jack? That gives me 3. Okay, so my mental math is correct. So, let's put this in the slope formula. Keep in mind, folks, that this is in meters because it is the position function. So we're going to use our standard y2 minus y1 over x2 minus x1. So, we will use 2 meters for the y2 and 3 meters for the y1. And we will use 4 seconds for x2 and 3 seconds for x1.
Nice line.
What? Oh, thank you. Thank you. Thank you. Always got to point out my mistakes. Okay, so this will equate to negative 1 meters over 1 second, which will bring us to negative 1 meters per second. That is, folks, the average velocity in the time interval 3 to 4. Hey folks, thanks for watching. I hope you learned a bit about calculus today. I know I did myself, and that you approve of my teaching methods. And other than that, folks, have a nice freaking day. Who do you think you are? Running round leaving scars, collecting your jar of hearts, tearing love apart, and you happen to find your soul to the soul of your soul. What did you mean to me, collecting your jar of hearts?